demo involves carbohydrates. Carbohydrates, like these guys, are made of, just like they sound, carbon and hydrate. Well, when you need to get hydrated, don't you drink water?
Yeah.
So they're carbohydrates. They contain carbon and water mixed together. So carbohydrates. So what we're gonna do is, well, look at this, by the way. Notice, this doesn't look much like carbon. Almost completely opposite of what carbon looks like. So it's funny that, does this really contain carbon? We're saying it does. Well, why don't we see that carbon? Why don't we get that carbon out? But in order to get the carbon out of the carbohydrate, well, what do we have to get rid of? We have to get rid of the water. So if you have a carbohydrate and you get rid of the water, well, what are you left with? What are you left with, guys?
Carbon.
Carbon. So we're gonna get rid of the water. We're gonna do that using a catalyst, sulfuric acid, which is a very nasty customer. I like to say it's like the drool from the Alien, the drool in that Alien movie, or Aliens, or Alien 3, or Alien vs. Predator, or it's the drool. It eats through the bulkhead of the ship. Very nasty acid. Produces nasty fumes. That's why you guys are not handling it, my kids are not handling it. Okay, but what I'm gonna do is I'm gonna use this as a catalyst, because if you put sulfuric acid into carbohydrates, well, I guess that's what H2SO4 is. What's H2SO4? It's for dehydrating carbohydrates. So I've got thermometers in here. This one is 21 degrees Celsius. This one is 23.4. These cans are at different temperatures for some reason. I'm not sure why. They're at different temperatures. And what I'm gonna do is I'm gonna make a little pit, little depression in the middle of each one. And I'm gonna pour in each one a whole bunch, 50 milliliters of H2SO4. So it doesn't have to be exact, I'm just gonna get it approximately 50. And we'll see what happens to the temperature, and we'll see if the carbon can come out of there, if we can see the carbon that's in there. I'm gonna do that one, then I'm gonna start this one right away. So keep an eye on the first one, 50 milliliters, that's quite a lot. That's quite a lot of H2SO4. And I'm just gonna go right ahead and start the second one, just to save time. There's another 50 milliliters. Oh, and why do I have French toast? Well, hasn't your mother ever told you, or maybe your father, that, oh, that stuff, that French toast, it's all sugar. So let's see if that's true. I don't need as much. I'm gonna pour a smaller amount in here. I'm gonna try to write a letter on the French toast. Let's see, that's probably enough. Try to write a letter on the French toast. Oh, that didn't come out so great. That wasn't as good. And then one more thing I don't usually do. Well, I wonder if there's carbohydrates in honey. Let's try to pour some sulfuric acid into some honey. Okay, this is one I have not tried actually ever before. So we'll see how this one works out. I'm just gonna pour about 25 milliliters in this honey. So if it has a lot of carbohydrates, well, we should get some kind of reaction. Oh, we're seeing reactions now. Okay, we're seeing reactions. So I'm gonna shift out of the way. I'm gonna shift out of the way. You notice what's happening? What's coming out of there? What's coming out?
A monster.
What's coming out? It's a monster rising out. So I've also got traditional thermometers as well. Let's see, that one is saying, oh, let me just stick this into there. Let's get a good temperature in there. Look at it shooting up. You see that red shooting up? Some of those fumes rising out are actually the sugar, and there's a little tiny bit of the sulfuric acid. And let's see, what temperature is this one? We'll get down in there. It's rising up. The problem is keeping the thermometer down at the bottom. It's tricky. Oh wow, this is over, look at this. This was over 90. Look at this. This is way up near the top. 100, 110, uh-oh. I better pull it out. Look at that. So, I'm gonna go on the other side. So what you see here are carbon sort of, Oh, there we go, good. These are kind of like carbon asteroids, okay? The temperature inside this, let me get this back inside, it's pretty high. It's up to 110. I'm gonna pull that out before it bursts the thermometer. Look at this, it's very lightweight. It's a chunk of the carbon. This carbon was in that carbohydrate. All of this came out of that can of sugar, okay? So now, notice this one, it says on the digital thermometer, it says 136. That's a pretty good measurement. This one fell out. 137, it's still going up. This one unfortunately fell out. I wonder if I can get temperature in there. I think we missed the high temperature. Is French toast got a lot of sugar in it? What do you think? What do you think? And then, what about this one? Okay. Is the honey reacting? Well, it's turning black, but not a strong reaction yet. Let's see if that keeps going. Let's see if that one keeps going. I'll take this out and stick this here. Oh, there's one more I want to do. Problem is, this is hot. This is very warm, very, very hot to the touch. It feels almost as hot as boiling water. This one is hotter than boiling water. It's in the 140s Celsius, which remember, is like way over 200 degrees Fahrenheit. Okay, this is another carbon asteroid. So notice, all of that carbon came out of the carbohydrates that were in that can. And we have one more quick one I want to do because there's a difference in grain size. This is your regular granular sugar like you put on cereal, let's say. This one is powdered sugar. So powdered sugar has a smaller grain size. This is also dextrose. I'll do it right there. This is also the dextrose. So I'm going to pour sulfuric acid into this one, and we might get a quick reaction. I guess I can use this thermometer again. And I'm going to pour in a full 50 milliliters. I'm going to pour in the same as I did in those into this wasabi peas can. This one. Okay, there's another 50 milliliters of H2SO4 going into there, and it says right now 27.6 degrees. Let's see what it goes up to after the reaction. Remember, you can tell if it's an endothermic or an exothermic reaction by what happens on your thermometer. This one's still in the 140s. Actually, I'll stick it in afterwards. This one's still in the 140s. I gotta get out of the path of these fumes. That one happened really quickly, right? It started much faster, right? So the only reason to shift is if the fumes are heading straight toward you. Look at all that. Look at all that. Now this is actually mostly just water. This is the water that is leaving the carbohydrates, and there's the carbon. It's going wherever I go. It's aiming toward me, right? Let's see what the temperature is here. Let's see what the temperature is on here. It's going up 117, 119. It's in the 120s. So this might not have been quite as high a temperature as this one was, which is still showing 140, or maybe it's still getting there. But it happened much faster. Why? Because it's much smaller grain sizes. And again, it would go off this thermometer. That's why we have the digital thermometers. Oh, now it's in the 130s. It's up in the 130s. So notice this carbon monster, I'm going to smash it on the ground. Watch. It's a carbon monster. And look at that. Why is it so fluffy? Because it's full of all the bubbles where the air went in. Okay, when the steam was coming out, it frothed it up like a foam. So that's why this is so light. It's very, very low density. And how can all this come out of there? Because it's been frothed up, that's why. Okay, and now it's getting to 138, so it's actually pretty similar. This one got to, what, 147, I think? And this one's getting, right now it's almost at 140. Let me see what the maximum temperature is. Let's just film till we get a maximum temperature on this. And the honey, sadly, is just turning black. I don't think we're going to see any dramatic reaction. You probably don't want to use this honey Lucy anymore. Probably don't want to use it. This is not a good syrup to put on your French toast. Not a good one anymore. I don't think it'll react if I pour it out like that. Okay, so now you can see that there really is carbon in carbohydrates. Even though they have a very, very kind of white or brown appearance, if you take out the water, this is what is left, the carbon. 147. So it's funny, they reach the same temperature. This one's still going up though, so it might get a little higher. Interesting. I'm gonna call it at oh no, it's still going up, 147.8, 0.9. I'm just gonna have to call it at 148 degrees Celsius. And if you're wondering what that would be in Fahrenheit, let's switch this over to Fahrenheit. And that is, oh yeah, 300. It's just getting to 300 Fahrenheit. So it doesn't sound as hot in Celsius, but that's a really high temperature. All right, thank you guys. Thank you everybody. All right, the Hydrate Lab. We are going to be using a beautiful blue chemical called copper sulfate, CuSO4. Beautiful, beautiful blue chemical, which is located in these beakers. There it is, the beautiful copper sulfate. Okay, copper sulfate. But the problem with copper sulfate is that it's not really blue. So let's explain that. Sulfate is a polyatomic ion. There it is, SO4, 2 minus, sulfate. Okay, in order to neutralize that minus, it needs a plus. This is an anion, it needs a cation. That's copper. Copper usually has a positive 2. Put that on to the sulfate, you've got copper sulfate. Okay, that's the one we're using, the beautiful blue chemical, but it's not blue. Unless water comes along. I like charges. I like negatives and positives. I like any charge. Oh, this has charges. I'm gonna stick to that. Oh, over here it's got a charge. I'm gonna stick to that. That's called a hydrate. When water begins to stick to things, that is a hydrate. Hydrates are salts that have water attached to them. Well, when it's got water attached, it does look blue. So we're gonna take this chemical and be mean to it. We're gonna get rid of the water that is attached to it by heating it up on a hot plate, and the water is going to fly off, and then we lose that beautiful blue color. We are left with just a boring, drab, kind of off-white chemical copper sulfate. Okay, the Hydrate Lab. Okay, I've plugged in my hot plate. It's gonna get hot. I gotta be careful with that. Okay, we're using this beautiful blue chemical, the copper sulfate. Okay, beautiful poster child for chemicals, and we're gonna destroy it. Okay, here is my crucible. Okay, a crucible is a little device, a little cup that you can take to extreme temperatures, and it can take it. And you put something inside, and that will be taken to extremes. You see how it behaves under extreme conditions, like the Crucible by Arthur Miller. We need to know the mass of the crucible, so write that down. That would go there. Mass of the crucible, A. Write that down. Okay, notice that I had tared my balance. Tare is the same as 0 on this one, okay, before measuring that. Now I want to measure out I want to use a beaker. I'm going to tare that, ignore the glass, measure out about 3 grams. You know what? I'm not going to worry about getting it exactly 3. Instructions say 3. There we go, 3.48, whatever, close enough. So write that down for the hydrate. This is a hydrate because that's why it's blue. Copper sulfate is not actually blue unless it has water. So that's the mass of the hydrate. Now I want to pour that into my crucible and get the total mass, or I could have added those two to get it. This is the total mass. The reason I want to know this is because that will be, oops, notice how I didn't tear it? I better tear it with nothing on it. get the total mass like this. So 22.96 is the total. I could have added them, but there's less rounding if you measure it directly. That goes in B. Now I'm going to take this, put it onto the hot plate, and we're going to watch the color fade. I'm going to put the camera above and leave it running, and I might fast forward through some of this. When the blue is gone, that means that the water is gone, and then we'll have a dry salt. I'm going to zoom in a little bit. Let's see if I can do this better. There we go. So now watch what happens with this color. It's actually, I feel the heat rising off here. I'm going to be very careful. I'm only going to handle it with tongs when I need to move my crucible. I'm going to grab it on one side and have it firmly. Okay. I'm going to leave this camera running, and we're going to see the color fade. Then I'm going to come back and get the mass of the crucible with the dry salt in it, which will be when it has a color kind of like this, kind of bland and drab like most chemicals, not this beautiful poster child chemical. Okay, so I'm going to leave this running, and it takes approximately maybe less than 15 minutes, and then we're going to see the mass of the dry salt. We'll be able to figure out how much water has been lost. Okay, it looks good. I see all the blue is gone. So now I'm going to take it off. I'm going to take it off. And normally we would let it cool, okay, for 4 minutes. Okay, but I'm a little pressed for time because I'm making this video a little before class. So we want to know what the crucible and the dry salt is. So what I'm going to do to protect my little balance, because this is a very hot crucible, I'm actually going to take 2 of these pads, insulating pads. Okay, of course they have a bunch of mass, a lot of mass, and I want to tear those away. So now it's ignoring those, and that should be enough to protect the delicate circuitry from the heat. So I'm putting this on here, and now this is the mass of the crucible with the dry salt. That's the dry salt. There's very little blue in there. Very, very little blue. 21.67. Sometimes you have to wait for it to 0.69. That is what goes right here. Okay? And then, if that was the hydrate and that was the dry salt, okay, I'm sorry. For this number, you can subtract your crucible. You can subtract your crucible to get just the dry salt. Once you've got the dry salt and you know how much hydrate we put in, that 3 point something grams we put in, okay, then we can find how much water was lost. But since we lost water, we were kind of mean. We took this beautiful blue chemical. Look, we took this beautiful blue chemical and turned it into that. Kind of sad, right? Okay. Now we're going to give some of that back. We're going to add a few drops of water, just very few. Watch what happens. 1, 2, 3. I actually added 4 by accident. So notice that that gives it back its blue color. Now it's like rehydrating, just like when you want to get hydrated, you drink some water. Well, now this chemical is sort of drinking up the water, let's say. So now if I put it back on my hot plate, I can get rid of that. Okay, if I get rid of that, again, that little bit of water I added shouldn't take too long, then that will double check my initial number for the crucible and the dry salt. I can write it on the side here, and then these two numbers should be about the same, really, and whichever one is lower actually has less water. That would be a better one to use for all my calculations. Okay, so this is a double check, and I'm going to put the camera here to watch that fade. This should be very quick, and then we're going to take the mass one more time, and that's it for the experiment. Okay. Now it looks like the color is gone. So I am done with my experiment. What I'm going to do is I'm going to, first of all, unplug my hot plate. Unplug that. It'll start to cool off. I'm going to take the crucible off of here, okay? And we're going to tear the balance just to make sure with those two pads on it, insulating it. And I'm going to take the mass again. This should match. This would be our double check, 21.67. This would actually go right here. I'd write it on the side as a double check of this one. Whichever one of those two was lower means it has less water, that we got it drier, and that would be a better one to use for my other calculations. Okay? So notice that this is what copper sulfate really looks like, and yet this is what it looks like hydrated. Okay? It's kind of sad. We kind of destroyed a beautiful chemical here. Okay? So, and then there's the calculations, kind of cookie cutter.